collaboration. This is a collaboration with my advisor, Jan Hoffman. And one of the hottest topics in program verification is to do resource analysis. We want to analyze the performance of programs, such as the time, the memory, or even the power it will use. So among the tons of techniques for resource analysis, I'm very interested in the worst case analysis. In other words, if we have the worst case performance of a program, we can reason about its performance bottlenecks. We can detect algorithmic complexity attacks, or even to identify timing sense So here is a concrete example of worst case analysis. So take this one of the best programming languages in the world, PHP, and somebody identified a potential denial of service attack several years ago. So how can we confirm this is a true bug? We need to submit a concrete exploit, and later on we realize this is caused by hash collisions. So using this concrete worst-case input, we can reproduce the attack and figure out where the bug is, and then fix the bug. In this example, worst-case inputs are very instrumental to understand and fix performance bugs. So how can people do this kind of worst-case analysis? There are two major communities, at least in the programming language research. One is the dynamic approaches, such as fuzz testing, symbolic execution. These methods are very flexible and universal in the sense that they can be applied to industrial strength language like Java, and they can handle almost all the program features. But they are potentially unsound in the sense that the resulting inputs might not trigger the worst-case behavior. On the other hand, there are also a very large community of static approaches like type systems, abstract interpretation. A big advantage of this method is that they can provide sound upper bounds on the resource usage, but they are potentially not tight because they usually don't provide concrete witness, so the upper bound might be too conservative to be useful. In our paper, we want to combine the advantages from both the dynamic approaches and also the static approaches. So we proposed a type-guided worst-case input generation algorithm. On the one hand, we prove soundness and relative completeness of our technique, and on the other hand, we also devise several heuristics to improve scalability in practice. To be more specific, our algorithm is based on resource-aware ML, which is a resource-aware version of a considerable subset of OCaml. And to generate concrete witness to trigger worst-case behavior, we utilize symbolic execution. And as our title suggests, the idea is I want to use the information from resource-aware ML to guide the symbolic execution. Now I have talked about why we are interested in worst-case analysis and the basic idea of our approach. Before diving into the technical part, let me just introduce some background about resource-aware ML. So resource-aware ML is based on amortized resource analysis, specifically the potential method, which is a very classic approach for algorithm complexity analysis, which is dated back to 1985. The basic idea is that we can treat the program transition as a graph. The node in the graph are program states, and the arrows stands for transitions between the states with actual costs. Then how can we reason about the performance of this program? We can assign a potential function. Here we use the phi as a function. And it assigns a non-negative number to each program state. And what's more, we add more constraints on these potentials. Specifically, we require the potential of a program state to be sufficient to pay for the actual cost of the next evaluation step, as well as the potential of the next program state. So for example, here, we require that the potential of D2 to be greater than or equal to the cost between D2 and D3, as well as the potential of D3. In this way, the initial potential phi D0 can be treated as an upper bound on the resource usage. Resource-aware ML integrates the potential method in its type system. The potential at a program point is defined by a static annotation of data structures. For example, a list of length n annotated with a non-negative number q has q times n units of potential. In other words, each element in the list can carry q units of potential. So now let's take a look at the program on the left side. It's written in OCaml syntax, and it defines a recursive function, L pairs. It takes as input an integer list L, and it does some operations, and at the end it returns all the adjacent ordered pairs of integers in the original list. Suppose that we want to reason about its memory usage, and we assume that each of the nil, count, and pair constructors costs 2 memory cells. After some sort of analysis, we can know that the actual cost of the worst case cost of this function is 2 times the length of the input list L plus 2 memory cells. So how can we represent this upper bound in the type system? We can use just some annotations on the actual arrow type. So here, the argument type is a list of integers. The capital L stands for list. And here is the annotation 2. The 2 here just means each integer in the list can carry 2 units of potential. So similar for the result type, except that the annotation is 0, which means that the result value cannot carry any potential. You might already notice that there are 2 extra numbers on the arrow, which is 2 and 0. These 2 numbers represent constant potential before and after a function call to this function. So if you want to call the function L pairs, you have to provide 2 extra units of potential. So how can we verify that this function have this type signature? We can do potential analysis. So at the beginning of the program, we have 2 times the length of the list L plus 2 units of potential, and then we do a match on L. If the list is empty, then we return an empty list. And as we know, the empty list will cost 2 memory cells. And in this case, the potential evaluates to 2 exactly. So it's sufficient to pay for this cost. In another case, if the list is non-empty, we map x1 to be the first element and xs to be the rest of elements. Now, the potential we have is 2 times the length of xs plus 4. You get 2 extra potential from the integer x1. Then we have another match expression, and for the empty case, it's similar. So let's proceed to the non-empty case. Now, in this environment, we have 2 times the length of xs prime, which xs prime is a tail of the list xs. Now we can get 2 more units of potential from x2. So we have the plus 6 here. Now we have this conditional expression. As we know, the pair and the cons constructor will cost 4 memory cells in total. So after that, we'll have 2 times the length of x's prime plus 2 units of potential left over. Now what we have is a recursive call to the function itself. From the type signature, we know that the potential phi 3 is exactly what we want, or what is required to do this recursive call. So we can conclude the proof. In other words, intuitively, we can treat the type signature as an inductive hypothesis, and the nil cases are the base case, while the recursive call cases are the inductive case. Here's an example of typing rule. Gamma is the typing context, and sorry. Again. Wait. Where's typing rule? Okay. So we have this Q and Q prime just as the two constant potential before and after the evaluation. You might notice this is the rule for the matching expression on list. And in the non-empty case, you'll get P more potential from the list if the list is annotated with P in each element. Now we have talked about the resource-aware ML. So then I want to say something about how we build our algorithm based on this type system. So our type-guided worst-case input generation is based on symbolic execution. The basic idea is that we can search all the execution paths through the program, record the path constraints, and then compute resource usage. After you have all this information, you can determine which one is the worst-case one. Formally, you have a symbolic environment gamma, which maps program variables to symbolic data structures, and your program is then expression E, and the result of the symbolic execution is a pair of path constraints and a symbolic evaluation results. So for example, there are two rules for the conditional expression for then branch. You can evaluate the expression in the then branch and collect its path constraint and the result. Then for the conditional expression, you can add the predicate to the set of path constraints. So for the else branch, it's similar, except that you need to add the negation of the predicate. So let's go back to the arrow pairs example. If we do a symbolic execution through the program and we collect all the paths, you can see the worst case one is that we always execute the then branch of the conditional expression because this branch have more memory allocation. So intuitively, you should always choose the then branch. Actually, an example of a worst case execution path for input list of length 4 is that the first integer in the list is smaller than the second one, and int 3 is smaller than int 4. After you collect this constraint, you can invoke an SMT solver to find a model for that. For example, 0, 1, 0, 1. You might already notice that in the symbolic execution formalization, there is a lot of non-determinism. For example, in the conditional expression, if you cannot determine the actual value of the predicate, you have to try the both branch, and this will lead to state explosion. So here comes the major technical idea of our work. We can use the information about potentials obtained from the resource-aware type checking to prove the search space of symbolic execution. To see how this idea works, we return to this run example and recall that we have this type signature. Also, we symbolically execute the program with an unknown integer list of length 4. And it will proceed to the conditional expression. Now we have x1 mapped to the first integer, x2 mapped to the second integer, and x prime maps to the int 3 and int 4. We also know that at this point, the potential is 2 times the length of x prime plus 6, which is 10 units of potential. And in the then branch of the conditional expression, we also know that the pair and the constructor will cost 4 memory cells. So after that, we'll have 6 units of potential left over. And this is exactly what is required to do the recursive call. On the other hand, if we take a look at the else branch, you can determine that the potential 5-3 is also sufficient to do this recursive call. But actually, at the point of this conditional expression, we have 10 units of potential. So in the else branch, there's potential waste. In fact, you waste 4 units of potential. So our idea is that if an execution path does not have any potential waste, it must expose the worst case resource usage. So formally, in our system, we combine the typing judgment and a symbolic execution judgment. The blue ones are the typing judgment, and the orange ones are the symbolic execution. Besides proving the search space, our algorithm also enjoys theoretical guarantees. The first one is soundness. It just if our algorithm generates an input then the input will cause the program to consume exactly the same amount of resource as the inferred upper bound by resource-aware ML. What's more, we also prove some sort of completeness. It's complete modular constraint solving, in the sense that if there's an input of some given shape that causes the program to consume exactly the same amount of resource as the inferred upper bound, then our algorithm can find a corresponding execution path. Why is the completeness interesting? If the logic for path constraints is decidable and our algorithm cannot find a worst-case input for a given shape, it tells us the upper bound derived by resource-aware ML is not tight. So we hope that we can use this information back into the resource analysis to improve the result of resource bound inference. This kind of type-guided input generation is still non-deterministic in the sense that for conditional expression, the both branch may not waste potential, so you cannot prove any of them. But because we have soundness, we can just throw away some rules that we can totally forget about the else branch and only execute the then branch. If our algorithm can also return with some result, it's still correct by the soundness. A generalization is that we can enforce all the calls with the same shape of inputs to execute the same path inside the function body. And we have talked about the resource-aware ML and our type-guided worst-case input generation based on that. Now I'm proceed to talk something about evaluation. We implemented the algorithm to be integrated into resource-aware ML, and with support of some very useful features like higher-order functions, user-defined data types, and polynomial resource bounds. And we use the off-the-shelf SME solver Z3, thanks to Microsoft. Here's a selected list of benchmarks. We try our algorithm on sorting algorithms with hundreds of integers, operations on trees, and also insertion into hash tables. Here, ALG is our basic algorithm, and H1 and H2 are two heuristics. We can see that at least our algorithm is effective to generate worst-case inputs for these benchmarks. Let's go back to the hash table example for PHP at the very beginning. We use a customized resource metric for hash collisions. And we use this hash function from this PHP implementation. The program inserts 64 strings into an empty hash table, and our algorithm can very quickly realize that it should find 64 strings with the same hash key in order to trigger the worst case number of collisions. To summarize, we propose a type-guided symbolic execution algorithm for worst-case input generation. We develop our algorithm as a formal system, and we prove its soundness and relative completeness. As for the empirical part, we integrate our algorithm with resource-aware ML, and there's some experiment to show it's effective on benchmarks. It has some limitations. It only works for purely functional programs, only works for tight bounds, and it's highly dependent on resource-aware ML. So in the future, we hope to improve our algorithm to support more features, and more generally, we want to develop a theory for worst-case analysis. Thank you.
Plenty of time for questions, and let me remind you we have Slido also, so put your questions up on Slido, and we can think about that too. So do you have any questions?
So when you started talking about the type-guided aspect, you used it in order to deal with the path explosion problem. Is that right?
Sorry?
You used the type-directed aspect to avoid pruning away paths. Mm-hmm. Is that right? But have you just tried encoding the whole program as one giant formula and give it to the SMT solver and have it do the path pruning itself instead of doing it manually? Like bounded model checking style.
You mean you just collect constraints from symbolically execute the whole program?
Correct.
And just by comparing the cost of every single pass?
Correct.
I remember I think it's exactly the approach described in another paper in ISTA 2018. They proposed a tool called Badger, and I think it's exactly what they does, and we also compare our approach to them in the paper. Basically, we compare the quick sort as well as the hash table example, and the result is that we can generate the truly worst case inputs very quickly, and while their method can just need to run a fair amount of time and cannot guarantee that that's the truly worst case one.
More questions?
What if your tool is run on non-terminating programs? If the program does not terminate, what will happen?
That's a very good point. It's like, but basically, we hope our algorithm to deal with time complexity. So we first run resource-aware ML through the program, and if it can derive an upper bound on the program, then we do our worst-case input generation. So basically, because resource-aware ML is sound, so if you have upper bound on the time usage, then it must be terminating.
Okay, I see. But if resource ML cannot derive the upper bound, then you just do nothing.
Yeah, this is what I said about the limitation.
Could your system be used to generate denial of service attacks? Question from Slido.
If just for this simple hash function, I say yes, but it's still, so it's another question that if you have a huge system, how can you do analysis through this whole system? It's like you need to use some other technique to find the spot in the software which can cause the denial of service attack. Then we can extract the model.
Are there limitations on the kind of amortized analyses you can handle? I'm thinking here about like splay trees. I know splay trees are not normally functional, but you can write a functional version. But they have a very complicated amortized analysis argument. So is that kind of thing within the scope of your tool, or is that something you can't?
I say at least now we don't support splay trees, but it's in the future work. But we can actually deal with functional queues, which is another classic example in amortized analysis.
Okay. One last question.
So in your pair list examples, you use the input 4, right, to show the worst case of a list of length 4. How do you know 4 is the right number? Because if your implementation varies, you don't even know whether the worst case comes out at 8 or 12 or 16. The algorithm may not be totally parameterized by n. I mean, they may not exhibit monotonic behavior just with the size of it. It could be even number gets much worse than odd number.
Yeah, this is a very good question, and for us, it's also an open problem to explore. Just that, how can you see a bound is tight in whatever sense? So, yeah, we'll work on it in the future.
Okay, let's thank the speaker again.